Hello everyone, I'm Timothy, a high school math and physics tutor who is actively studying graduate level mathematics. In this video, I'd like to cover the tower of subgroups and its related concepts. Without further ado, let's begin. Let's take a look at the definition of tower, normal tower, and abelian tower or cyclic tower. Let G be a group. A sequence of subgroups G equals G now contains G1 contains G2 up to Gm is called a tower of subgroups. The tower is said to be normal if each Gi plus 1 is normal in Gi, where I equals 0 to m minus 1. This is said to be abelian or cyclic if it is normal, and if each factor group Gi mod Gi plus 1 is abelian or cyclic. Here we have the following setup to prove three different claims. Let f from G to G prime be a homomorphism, and let G prime equals G prime null contains G prime 1 up to G prime m be a normal tower in G prime. Let Gi equals the pre-image of G prime I. Let's look at claim 1. The Gi, where I equals 0 to m, form a normal tower. Because G prime I contains G prime I plus 1 implies the pre-image of G prime I contains the pre-image of G prime I plus 1, the sequence is descending. Then we can trivially verify the pre-image of a subgroup under a homomorphism is a subgroup, and the pre-image of a normal subgroup is normal. Here is claim 2. If the G prime I form an abelian tower, then the Gi form an abelian tower. According to what we proved in the last video, we get injective homomorphism f bar I from Gi mod Gi plus 1 to G prime I mod G prime I plus 1, defined by f bar I of Gi plus 1 equals f of G prime I plus 1. Since G prime I mod G prime I plus 1 is abelian, f bar I of bracket x Gi plus 1 bracket y Gi plus 1 equals bracket f of x G prime I plus 1 bracket f of y G prime I plus 1 equals bracket f of y G prime I plus 1 bracket f of x G prime I plus 1 equals f bar I of bracket y Gi plus 1 bracket x Gi plus 1. Hence, Gi mod Gi plus 1 is also abelian. Last but not least, we have claim 3. If the G prime I form a cyclic tower, then Gi form a cyclic tower. Similar to claim 2, we get an injective isomorphism f bar I from Gi mod Gi plus 1 to G prime I mod G prime I plus 1, defined by f bar I of Gi plus 1 equals f of G prime I plus 1, which means Gi mod Gi plus 1 is isomorphic to a subgroup of G prime I mod G prime I plus 1. Since if a group G is cyclic, there exists G in G such that G equals a cyclic group generated by G equals a set of all G to the power of n where n is an integer. If H equals to a set with only the unit element is a subgroup of G, then H equals the cyclic group generated by the unit element is cyclic. If H is not equals to a set with only the unit element, then define a set S equals a set with all n in integers where G to the power of n is in H. By the well-ordering principle, let D be the smallest possible integer in S. Since G to the power of D is in H, we have the cyclic group G to the power of D as the representative is a subset of H. On the other hand, for all H in H, there exists n in integers such that H equals G to the power of n. Consider n equals qd plus r, where 0 is smaller than or equal to r smaller than d, then G to the power of n equals G to the power of qd plus r equals G to the power of d to the power of q G to the power of r. Since G to the power of n and G to the power of d to the power of q are in H, then G to the power of r is in H. But d was chosen to be the smallest possible integer such that G to the power of d is in H, hence r equals 0. Therefore, n equals qd and h equals G to the power of n equals G to the power of d to the power of q is in the cyclic group generated by G to the power of d, which implies h is a subset of the cyclic group generated by G to the power of d. Thus, h equals the cyclic group generated by G to the power of d. This shows that a subgroup of a cyclic group is cyclic, and therefore Gi mod Gi plus 1 is also cyclic. Here are two more definitions about towers. Definition of refinement. A refinement of a tower, G equals G null contains Gi up to Gm, is a tower which can be obtained by inserting a finite number of subgroups in the given tower. Definition of solvability. A group is said to be solvable if it has an abelian tower whose last element is a trivial subgroup, i.e. Gm equals the set with only the unit element. So far I've shown the tower of subgroups and its related concepts. Thanks for watching. If you would like to follow my math journey, consider subscribing to the channel. That's it for this time. I'll see you in the next video.